In this lecture, we are going to discuss the scaling property, differentiation property, convolution property, and initial and final value theorems of Z transform. So, first looking at the scaling property. Now, if I have any signal xn and its Z transform is given as xz for the ROC, R1 is less than mod z is less than R2, and a to the power n xn. Now this is the scaling factor a to the power n with us, and it is multiplied with xn. Then its Z transform is given to us as x of a inverse z. That means wherever there will be z mentioned in the xz, instead of that z we can write a inverse z. Now the ROC will subsequently change as mod a R1 is less than mod z should be less than mod a R2. So this signal is scaled over here, and there will be a scaling at the ROC as well. Now where this a in this context is a constant, which can be either a real value or can be a complex quantity. Now to look at this, we have an example. A discrete time signal is expressed as xn is equal to 2 to the power n u of n minus 2. Determine its Z transform. Now we have been given this question that xn is equal to 2 to the power n u of n minus 2. Now in this question we will be utilizing two properties. Firstly, since it is mentioned n minus 2, we have to utilize the time shifting property, and then it is mentioned 2 to the power n, so we have to utilize the scaling property as well. So first we will be utilizing your time shifting property, and then subsequently we will be scaling that. So if I have this value xn, so this u n minus 2 is nothing but the time shifted property of your un. So we know that the Z transform of un is given to us as 1 upon 1 minus Z inverse. Sometimes we refer to it, or if we want to take the LCM, then we can have it as Z upon Z minus 1. So both are basically the same thing. So we can utilize the time shifting property. According to time shifting property, if we have u of n minus 2, then its Z transform will be Z to the power minus 2 into 1 upon 1 minus Z inverse. So subsequently we can put Z to the power minus 2 upon 1 minus Z inverse. Now after this we can utilize our scaling property, that is we can take this into effect, this 2 to the power n. So Z transform of 2 to the power n u of n minus 2 will give us, wherever, as I had previously said, that wherever we will be having Z in our Z transform, I will be replacing it with 2 to the with a inverse Z. So here the a is nothing but 2. So instead of this Z, as it is mentioned Z to the power minus 2, so wherever there is Z, I will be replacing it with a inverse Z. So here a is 2, so I can put 2 inverse multiplied with Z whole to the power minus 2, and similarly in the denominator we have Z inverse, so I can put 2 inverse into Z whole to the power minus 1. So if I multiply this, if I take this 2 inside, then it will be 2 square, which will be equal to 4, then Z to the power minus 2 upon 1 minus 2Z inverse. So this will be my ROC. This will be my Z transform. Now next question given to us is, using scaling property, determine the Z transform of a to the power n cos omega naught n. Now the value of Z transform of cos omega naught n can be given to us as 1 by 2 z upon z minus e to the power j omega naught plus z upon z minus e to the power minus j omega naught. So sometime this is referred to as the value of cos omega naught n, and sometime we take the LCM and then find out that the z transform value is z into z minus cos omega naught upon z square minus 2z into cos omega naught plus 1. Now this value comes after taking the LCM of these values or these values over here. Okay, so if I multiply it with a to the power n, so it will be scaling the output. So for scaling, we know that wherever there will be z, we can multiply it with a inverse. So we have a z over here, so we can multiply it with a inverse. We can multiply here with a inverse. We can multiply here with a inverse z whole square, we can say, and here also we can multiply with a inverse z. So in this way, if we take the LCM of all the values, it will result as z into z minus a cos omega naught upon z square minus 2za cos omega naught plus a square. Now as we have done over here, we can also do it directly with this relationship as well. So if we do not want in this type of relationship, so we can directly do it over here as well. So we can put a inverse z over here, and we can put a inverse z over here. We can put a inverse z over here, and we can put a inverse z over here, and subsequently if we take the LCM, it will result as this value only. Now next property over here is differentiation property. Now this is a very important property. Now if we have xn, its z transform is given to us as xz. Now if there is a multiplication of n with xn at the input side, then its z transform will be minus z into dxz upon dz. And if we are talking in terms of the inverse, or if we have represented our output or the z transform in terms of the inverse values, then nxn will be giving us a z transform of z inverse dxz upon dz inverse. So let's check out a numerical that determine the z transform of xn is equal to n square un. Now this n square un is given. It means that we have multiplied n 2 times. So we will have to utilize the differentiation property twice. Now if we expand it, we can say that xz will be the z transform of xn. Now instead of xn, I can put n square un. Now this z transform will be of n into n un. So from the differentiation property, we can say that xz will be equal to z inverse d upon dz inverse of z transform of n un. Now I have took this z transform inside. Now firstly we had this differentiation for this first n, and then I have taken this z transform inside. Now again this z transform is of n un, so I can say that this z transform will be correspondingly, we can utilize this differentiation property again for this, and we can say that this will be equal to z inverse dz inverse of z transform of un. So we have twice utilized this differentiation property. So firstly we have to find z transform of un. So z transform of un in terms of the z inverse is 1 upon 1 minus z inverse. So d upon dz inverse of z transform of un will give me this value 1 upon 1 minus z inverse whole square. Now this d upon dz inverse of 1 upon 1 minus z inverse will be basically nothing but the differentiation of u by v formula. So we will be utilizing the differentiation of u by v formula to obtain this result 1 upon 1 minus z inverse. So now this we have obtained, this is basically our equation 4 we have termed it, and we can put it in our equation number 3. So where was our equation number 3? Here was our equation number 3. So we have calculated the values till here. Okay, now we have calculated d upon dz inverse z transform of un. So that we have calculated. So whatever left is xz will be z inverse d upon dz inverse into z inverse into 1 upon 1 minus z inverse whole square. So again we will have to differentiate this value z inverse upon 1 minus z inverse whole square. So we will be again utilizing the u by v formula of our differentiation, and subsequently we will be getting the value 1 minus z inverse whole square minus z inverse 2 into 1 minus z inverse into minus 1 upon 1 minus z to the power minus 1 whole to the power 4. From this I can take 1 minus z inverse common. So whatever will be left behind will be 1 minus z inverse plus 2z inverse upon 1 minus z to the power minus 1 whole to the power 4. From this 1 minus z inverse I can cut one of the orders of this denominator, and subsequently we will be getting 1 plus z inverse upon 1 minus z to the power minus 1 whole cube and multiplied with this z inverse. So this will be my xz. So this will be my solution of n square un. Now next property that we will be utilizing will be convolution property. Now in convolution we already know that convolution of any two signals is given to us as sigma k is equal to minus infinity to infinity x1k into x2 n minus k. So we utilize this property to find the convolution of any two signals. Now what Z transform does is it makes our task of calculation a bit easy. So what it does is, if I have any signal x1n and its Z transform is x1z, and x2n we have its Z transform is again x2z, and my xn is given to us as convolution of x1n and x2n, then its Z transform will be given to us as xz, which will be nothing but x1z multiplied with x2z. That is the Z transform of this x1 multiplied with the Z transform of this x2n. So this is utilized in your Z transform. So it and if we want to calculate of the convolution of any sequence, firstly we can say that we can find the individual Z transform of both the signals, we can multiply them, and then we can take the inverse of that particular multiplication. Okay, it will result in xn, and that xn will be nothing but the convolution of your x1n and x2n. Now here we will be utilizing the property to find the Z transform of this xn, which is given to us as n into minus 1 by 2 to the power n un convolution 1 upon 4 to the power minus n u of minus n. So here the first function is, or we can say that x1n is n into minus 1 by 2 to the power n un, and x2n is 1 by 4 to the power minus n u of minus n. So the first function, that is x1n, we can see that this signal over here is scaled first, that is minus 1 by 2 to the power n, and then we have to utilize the differentiation property as n is multiplied over here. So firstly we will have to calculate the Z transform of un, that we obtain as 1 upon 1 minus Z inverse. So and then we can scale it by minus 1 by 2 to the power n, that is by multiplying wherever there is Z with minus 1 by 2 to the power minus 1. So we have done it over here to obtain Z upon Z plus 1 by 2. Now this Z upon Z plus 1 by 2 is nothing but the Z transform of minus 1 by 2 to the power n into un. Now the third thing is it is multiplied with n. So this multiplication of n gives us, we have to utilize the differentiation of Z transform. So as previously mentioned, we have two type of we have two representation of Z transform. In the previous example we have utilized the inverse terminology. Now here we will be utilizing the Z terminology. So for Z terminology we have this x1z, which is given as minus z d by dz of z upon z plus 1 by 2. Now if I take the differentiation of this z upon z plus 1 by 2 and multiply it with minus z, it will give me the Z transform of this x1n. So I take the differentiation of this value d by dz of z upon z plus 1 by 2 by the same u by v formula. So it will give me the value minus 1 by 2 z upon z plus 1 by 2 whole square, where the ROC has the value mod z greater than 1 by 2. Now as it is resemblance from the denominator below. Now next we have this second function, that is x2n. Now this x2n is given to us as 1 by 4 to the power minus n u of minus n. Now this is a bit simple, but here again we will be utilizing two properties. One will be the scaling property and the other will be your time reversal property. Now firstly we already know that the value of un is 1 upon 1 minus z inverse. So we scale it by 1 by 4 to the power minus n un. We can put the values over here, that 1 upon 1 minus into 1 upon 4 to the power minus 1 into z to the power minus 1. So subsequently we will be getting 1 upon 1 minus 1 upon 4 z inverse, so which will result in z upon z minus 1 by 4. Now after this we will be utilizing our time reversal property. Now according to time reversal property, if I have such type of signal, then I have to put z inverse instead of your z in the z transform. So instead of x2z we can put z inverse wherever there is z. So z inverse upon z inverse minus 1 by 4. So subsequently, and the ROC, as it is mentioned that previously my ROC would have been mod z greater than 1 by 4. So by reversing, this ROC will change, since we will be changing all the z into z inverse. So here I will be changing the value of z into z inverse, and it will yield me 1 upon z should be greater than 1 upon 4, which will ultimately give me that mod z should be less than 4. Now this x2z is equal to minus 4z upon z minus 4. Now as we have seen that by the property of our convolution in Z transform, my xz will be nothing but the multiplication of this x1z and x2z. So I am going to multiply these individual x1z and x2z to obtain 2z square upon z minus 4 into z minus 1 by 2 whole square. Now here if I take both these ROCs into consideration, one of my ROC was mod z greater than 1 by 4, which is converted into mod z is less than 4 for this time by this time reversal property. And previously we had this value of ROC mod z greater than 1 by 2. So if I combine both these ROCs, then my ROC that will be obtained will be 1 by 2 will be less than mod z, and which will be less than 4. So it will be forming basically a ring where the outer ring will be at 4 and the inner ring will be at 1 by 2, and the area between those ring will be representing my ROC. Now next will be my initial value theorem. Now in this Z transform, we have this initial value theorem, and it is said as if xn is a causal sequence, then its initial value is given by the above expression. Now this above expression is nothing but it is telling me about x0, and it tells me that it will be equal to the limit z tends to infinity xz. And similarly for the final value theorem, if I have xn and its z transform is xz, then my final value, that is x infinity, will be given as limit z tends to 1 into z minus 1 into xz. Now if we look at the numerical based on initial value and final value theorem, we can see that we can find the initial and the final values of xn if the z transform is xz is equal to 2 upon z square plus 1 by 6 z minus 1 by 6. So this is the numerical given to us. So in this we have to find the initial value, so we can utilize this property of x0 is equal to limit z tends to infinity xz. So if I put this value of z is equal to infinity in this equation, we will be having 2 upon infinity. So anything upon infinity will give us 0. So my initial value will be 0. Now to find the final value, it is given limit z tends to 1 z minus 1 into xz. So I can put this value of 1 over in this xz and this z minus 1, so 1 minus 1 will give me 0, and if I put this 1 over here, it will give me 0 upon some particular value. So my this value of x infinity will be giving me an output that is equal to 0. So by my initial and final values of for this given xz will be both zeros. Okay, thank you.